Okay, I'm going to share the screen. Okay, I'm sharing the screen now. So I'll just do a quick recap. Okay, so we're building a regression model. Currently, we only have linear regression. We're reading in the wine data, right? And so we've done all of this. We've transformed all of our data into torch tensors. We did standardization, and I believe currently that this is giving us slightly better results than without. And the reason why I believe that is that I introduced the R-square metric, okay? And the R-square metric on the test set went from 20 to 28 when I did standardization. Now, in general, when you're building a model, it might be a good idea to print out the R-square for the train set, but really the thing that's important is on the test set, okay? Now, another thing that I'm going to do now is, the last thing that we were doing is we were printing the test set, the real and the predicted values, and we can see that in general, these values are all, they're float, but they are all kind of like 6, 5, right? There's no decimal part, whereas with the predicted ones, we do have that decimal part. So how do we deal with that? We have to think about that one. We could round and keep it as float, right? If we round and keep it as float, then we would get 6.0. Another approach could be to typecast it to int, but then we're going to lose the decimal part. Do you see what I'm saying? So there's a couple of things we can do. If you guys can find a torch function for rounding, that would be really great, because then we can try that. Okay. So think about that, right? So we might want to add that into our architecture. Okay, the other thing that we did is we've created a tool for visualizing all the data in one shot. And basically, the goal would be that we only see one color, so they would be perfectly matched. Currently, we can see that I think the blue is the predicted, and they're not going as far as the ranges. So we got to think about that. All right. So yeah, so that's kind of the summary. So the next thing we can do is oh, I remember now. What I want to do is I want to rerun everything, because if you remember, I have what I call the poor man's tenfold cross-validation. So let's try another split of the data set, and maybe that one will give us slightly better results, right? So that's what we want to try out. So I'm going to go ahead to the beginning of the code. And I'm going to click kernel, restart and clear output. Okay, oops. Taking a while. Why is it taking some? Taking an error here. Okay. Okay. Got, yeah. Did you guys get a problem too? Let me restart the whole thing. All right, so cross your fingers that this works. All right, so I'm gonna clear the output again. Huh? My R-score went up by 1. Went up by 1. Okay, So cleared, okay, so good. So like I said, I'm just trying to rerun everything with a different random split. And this is what I was talking about. As we start doing this, we're always splitting, and that's kind of a good approach. Okay. There's our wine data, so that's looking good. Correlation coefficient matrix, that's good. Doing all the processing. Okay, so this split should be a little bit different now. Okay. Hey, it's training. Now, obviously, I'm only giving it a few iterations. We may need to give it more iterations. Sometimes one thing that's really useful is to change the learning rate to another value. Okay, so we might try that. But let's see what our score I get. Huh? The same, yeah. So just try it. We're all doing this. Hopefully, someone will get a better score. Obviously, we do have a few things to try, such as a better architecture. All right, so it finished. So now I'm going to try it out. And the R score is still 0.299. Okay, we're going to look at the predicted values. There they are. There's a lot to look at, so we want to visualize it with our little graph, which is gone here. So I guess when I restarted this, I lost it. Oh, that's wonderful. All right, do you guys still have it? You can yeah, I lost mine, unfortunately. But anyway, all right, so one other thing we're gonna try is I'm gonna go in here, right, into the architecture, and I'm gonna try to round this. So let's do ypred is a tensor, huh? Yeah, I'm gonna round it. Sorry? Yeah, that's what I'm gonna try to do. So torch dot round, and it takes ypred as an input. Make sense? This predicts a value basically. If given a vector, it should round all the values in the vector. So we should not need to do anything else. So let's just see what happens. So the idea here is, remember what's going on. The model is going to still predict the values, but now it's going to round the output. And that output is what's going to get compared to the real value. Do you see that? So the weights are going to be adjusted in a sense so that it tries to mimic what the real data is. But before, the model didn't have the power to round. So it would always give you 3.7, 3.5, something with decimal values. But now we're giving it the power to give us a 5.0. Do you guys see that? So let's try it out. Have you guys tried it already? It's worse? Okay, it's worse. Okay, well, all right. I'm just trying things out. Huh? Yours was better?
Well, I did my rounding though outside of I did my rounding when we're appending to the list. So it doesn't actually
In the
change
test-
the value it's predicting on it. Yeah, when,
Oh, you're doing it after the prediction,
yeah,
after the, but then that's not, okay, I see what you're doing. And the
Well,
R square goes up, so
um,
you would have to do that rounding, yeah, I can see the loss is not great.
it doesn't change my R squared particularly, but it makes the chart look better because all of the decimals that
Yeah,
you know what I mean? It
Yeah, yeah.
chops off the.
I get it. Yeah, I can see the loss is not working. That didn't work. So let's try. I still think it could work. We just have to improve it. Let's try something else. But yeah, I can see the loss was pretty bad there. Yeah, so that's a pretty bad R squares. Okay, so back to the drawing board then. But I don't think it's a bad idea. I think we just gotta tweak it. All right, so we're gonna scrap this for now. I'm just gonna comment it out. And let's try another approach. So return ypred is what we have, right? This is a tensor, so let's try it returning an integer directly. Like, let's just see what happens there. So that should be 2. And then we can specify d type equal torch dot int32. This is actually what I'm doing. This happens. This is something you always do. We're gonna run our outputs through functions. You will see that later. We'll run it through softmax, sigmoid, tangent. So, you know, this is a common practice. But currently what I'm trying to do is I'm trying to get better results for my model. So the hope here would be that the values are integer now. So, you know, they should be, you know, just 3, 5, 6, etc. So let's try this out. See what happens. I think that's correct. So let's, no errors, okay. So I'm gonna run, you guys run it too, please. Gives an error. Really? Okay. What's the error? Element 0 of tensors does not require gradient, does not have grad effect. Okay. Okay, so I messed that up by doing the data type. So that definitely is worse than round. All right. So let's just leave it as is. And we're gonna need to come back to that. All right, so I think then the next step is let's just build another neural network architecture. How about that? Let's go from linear regression, which is not the best regression approach, to obviously to neural networks. So now a neural network is something that has more than, you know, has hidden layers, and it's gonna have activation functions, okay? So we're gonna start trying that out instead and see if that gives us slightly better results. So to do that, we're gonna have to create a new class, okay? Just like we created linregnet, now we're gonna create a new one and hope that that works. What was your R score when you did rounding outside?
It stayed roughly the same.
It wasn't better than?
No, because that.
Huh? 0.3, so it just went up slightly. So, okay, so then actually this is good information because we may not need to waste time on it, on rounding inside the network, because it's really not giving us better results, right? Do you see that?
Yeah, it just makes the graph look better.
It just makes it look better.
Because all the, like your orange and well, whatever 2 colors you have, if you got it right, there won't be any difference in where they.
The fraction, yeah. Okay, I see what you're saying. Yeah, but the R square didn't improve.
Yeah,
Oh.
so, 1 is the best result of the R square, right?
It's 1, yes,
Yeah.
and you are at
So
point
0.3 is the.
0.3, and I'm at 0.29. So it's actually, yeah, so I think the rounding idea is probably not gonna give us. Yeah, okay, so we're at 0.29.3. Okay, so you know what? Let's just hit it with a bazooka, right? And what do I mean by that? Let's use a neural network and see what that does. So, okay, so let's build a neural net. So I started with linear regression. The next thing I'm gonna try is what is called an MLP, a multi-layer perceptron, okay? Which is a neural net, definitely, but it's not deep learning, okay? Not yet, okay? So, and then we're gonna do the diagram by hand, just to kind of, for you guys to understand the differences. All right, so let me just make sure, yeah, it is recording. All right, so how do we do this? We are going to come down here to where we initialize our model. And now let's just comment it out. No need to delete it. And then copy this one. Okay. And we're going to create a new one. I'm just going to call it MLP. And give it an underscore or something, just like that. Okay. So I'm going to go ahead. And now I need to create this new class. Okay. That is going to reflect the new architecture. And I'm going to instantiate it. So I'm going to copy this down here. You see how this starts to make sense now, why we want to do it like this, because it's very, very nice, right? So I'm going to give this the name multi-layer perceptron, MLP. Okay. I'm going to change the name here to MLP underscore net, which I think is what I called it down. Yeah. All right. So I'm still going to standardize because we've determined, we feel that that improves from 0.20 to 0.28. Okay, so we have some evidence there. So now, I'll do a recap. So remember, we're using class inheritance. So that means that we're inheriting everything from nn.module into our new MLP.net class. We need to have the init and the forward functions. They just have to be there. And then when we do this command, we're initializing the inherited class. We are passing x means and x deviations, and we need to save them as variables in the class. And then this is where, of course, we're going to have to make some changes. Okay. And then down here, obviously, is where we define the architecture that we're doing. So this line stands because we take the x and scale it, basically, standardize. All right. So I'll do a recap by going to the whiteboard of what this represented. So the initial, when we did this as a linear regression, all we had was this, okay? That was the architecture, a linear function of 11 inputs connected to one output, okay? So let's go to the whiteboard. Okay, and let's think of what that neural network looks like. Okay. So that neural network, so if it's a linear model that is 11, 1, should look like right? So there's only one neuron here. There are 11 neurons, ... here. So this is going to be 11. This is going to be 1, and it's fully connected. Okay, guys? So it's fully connected. Most of our networks are going to be fully connected. Okay? Got it? That's the architecture that we did. But now, and this is, remember, the inputs and the outputs. It's all linear. Now I'm going to create a new one, and I'm going to say it is an MLP. So by definition, a multi-layer perceptron is a neural network of the following architecture. So I still have my input and my output, of course. And this is still 11 neurons. Okay, ... 11. Okay. This one is still one output neuron, 1. But now I'm going to have one more layer in between, okay? A hidden layer. So this is referred to as a hidden layer. Does that make sense? And I can define the size of this as I want it to be. And there's no like science to this. It's more of a best practices, right? Trial and error. But we could start with like, let's say, I'm gonna say, what do you recommend? Like, I could say 100. I could do that and just see what happens. But usually we have images that are really big as inputs, right? And so in that case, we almost always follow a funnel approach where the input is really large, then this is smaller, 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 like that. But because this is regression and we only have 11 inputs, it's really a little bit more tricky to decide. But in general, a good guideline would be that we want to have the simplest model possible. Okay, so let's just say since this is 11 inputs, I want to give it just enough flexibility. I'm going to give it 8 neurons. Why? I don't know. I just think I want to try that intuitively. Does that make sense, guys? All right, so again, these are going to be fully connected, okay? So I'm not going to draw all the connections because that's, too many, but you can see this is a lot of connections, a lot of weights now, right? And it's fully connected, and then these are fully connected as well. Okay, does that make sense? And that's why they're called neural networks, right? That's the architecture that we're building now. There's another thing that's going to happen here. This is still linear, okay? We need to have one more thing, which is basically to add something called an activation function. Okay, and usually you draw it by just adding something like this, and I'm going to say that the activation is sigmoid. Okay, what does that mean? It's a conversion of the values into something else. Okay, does that make sense, guys? So sigmoid is, we're going to look at activations later, but for now, just think of it as whatever the value is, it's going to be forced into a value between 0 and 1. Okay, let me redo that. So what's a good example of this? Remember sine and cosine, for instance? You guys have seen those functions, right? Take something in, and then it gives you another value, right? Those, it's basically something like that. So we're going to use the standard function called the sigmoid. We're going to do one class just on activation functions, where we look at sigmoid, tangent, ReLU. ReLU is actually the most common one, the so-called hockey stick. It's actually very intuitive to understand ReLU. All it does is if the values are negative, they become 0. If the values are positive, they stay. Do you see that? So it's called the hockey stick activation function because the graph looks something like this. If this is 0, right? So the values here are negative, the values here are positive, and then we're transforming them into this other scale. So all negative values basically are 0, and after that, they are not 1, they are the actual value. Yeah, so if it's a 2, then it's a 2. You see that? But if they're negative over here, they're always 0. Does this make sense? So that's why it's called a hockey stick. Looks like that. But that's what they do. These activation functions take an input and transform it into something else. This is what gives neural networks the ability to find other ways of analyzing the data. So for instance, let's say that our data intuitively looks like that. No, sorry, let me redo this. Let's just think of this as an example. Let's say that the classic example, we have this, and then we have this, right? So if we wanted to draw a line that separates this data, the x's from the zeros, do you see this? Okay, so that's probably the best intuition right now. What we built before, the linear regression model, cannot do it. Why? Because it can only draw straight lines. Do you see that? That's kind of the best intuition. Whereas now, the architecture that I'm with the MLP, or actually I can use another color. The MLP in theory, can do this. You see that? So that's the intuition, okay? Probably the best way to understand it is, so obviously the performance of the MLP would be better in this data set because it can draw the green line. Whereas the linear regression model that we built before can never draw the green line. It can only draw straight lines. And so it's gonna give us not a perfect model prediction. Got it? Does that make sense, guys? So this is what we're doing. So to be able to create a model that builds a green line, we need to then add a hidden layer, and the hidden layer definitely needs to go through some activation function, okay? Does that make sense? So that's what we're gonna code now. All right, so let's go ahead and go back to our code. I'm gonna stop this one. And now I'm going to go over here. All right. So how do we do that? So we know how to do the Lin regression one. Now we need to learn how to do the MLP in the code to reflect the thing that we were saying. So what did I say? I was gonna try 6, right? So then it's gonna be 8, was it? Okay, 8, sorry. So the input layer has how many neurons? 11. I said that the hidden has 8, and then the output has how many? 1. Okay. So I need to create that. So the way to do it is, this is 11, right? That's the input. But now it's not going to go to the outputs. It's going to go to the hidden layer. And the hidden layer is going to be 8. You see that? Now, additionally, we know that we're going to have an activation function there. So we're going to add that in. And I'm going to call it activation 1 to remind myself that it corresponds to linear 1. Okay, it's the thing that's going to follow after. Okay, so I'm going to need to initialize that using the nn dot module. So I'm going to say nn dot sigmoid. Okay, guys, do you see that? That's how I can add it. And then after that, I need to add the next layer, right? So I'm going to say self. Remember, this is only the declaration of this. We haven't actually created the architecture yet. So now I'm going to say self linear 2, okay? And self linear 2 then is going to be equal to nn dot linear. And now we specify the next part of the architecture. So this would be 8, 1. Very good. Yes, exactly. 8, 1. Very good. Do you see that? Now, the next question is, do you need to have an activation? Well, it would be then an activation for that 1 neuron, which I do want to have an activation that makes it integer or rounds it. Okay, so that's something that I need to think about how to do. Okay, but I still believe that idea might work. But let's just leave it like this. Okay, we can just leave it like this. And now we've defined the variables, but we haven't actually created the architecture yet. So we have to come over here, right, and think about it. Now it's sequential. So basically what you need to do is, you know, one after the other, okay? So ypred is no longer the value here because ypred should be the last thing. So we do the standardization first, then we take x and run it through linear 1, and that just gives us some variable. Now we could call it, you know, hidden 1 or something, but to keep it simple, just say x. It doesn't matter. Do you see that, guys? So x comes in through here, then it becomes standardized, then it goes through here, and then it comes here, right? And so it's being modified. Okay. So now the next step is what? Act 1. Very good. So again, I can just use x, and I'm going to say self dot activation 1. And what goes into activation 1? X again. Very good. Yes. All right. And then now, what do I do? Ypred. Okay, sure. Ypred equals self dot linear, oh, it's lowercase, right? Yeah. Dot linear what? 2 of x. Yeah, good. All right. Do you guys agree? Does this make sense for everyone? And just like that, we have built a multi-layer perceptron, and this is your first neural network of the course. Okay, not deep learning yet, but getting there. Okay, so this is, see how I said, you know, when we did Celsius to Fahrenheit, we had already done like 70% of the code, and then really just these little tweaks allow us to go from a linear regression to a multi-layer perceptron to deep learning and so on. All right, so we should be ready to try this out. So please go ahead and rerun all of this. I'm going to rerun it from the very beginning. And now we definitely have a neural net instead of linear regression. So let's see what our score we can get. Okay. I'll run this one. Regression. Okay, so here we instantiate model to MLP.net. We start the training at 14.6. Is it worse, Joey? It's worse?
Yeah, it ended with 1.0, a lost 1.0.
What is the R score? R square, sorry.
0.35.
Okay, so it's not worse. Why not?
Well, it's better, but
It's better, but not what you want. Well, I see a 0.19 in the loss. I've never had one of those. Well, it did go up a little bit, incrementally, right?
yeah, after that, you know, it's like going back up.
It goes up.
Yeah.
When I get this issue, I start to think that the learning rate needs to be tweaked a little. So we might want to add a 0 or remove a 0 on the learning rate. Also, I think I said 0.01, do a 0.3 or a 0.5, you know, 5 instead of a 1, more zeros. We need to play with all this. And like I said, what we're doing right now is exactly how it's going to be for you guys. When you have a new data set, you're just going to have to do things until it, you know, to try to get it to improve. All right. Oh, it finished for me. So let's see what happens here. 0.35. So I'm also getting what you're getting. Unfortunately, I lost the thing. I kind of want to, but I'll do it later. All right. So yeah. So we improved the results a little bit. What else can we do? So, I mean, that's all we're going to do for today as far as new content, right? So the next thing we can do is obviously a deep learning algorithm. But before I do deep learning, and I have an additional thing I'll try. But before I do that, what if we just change the learning rate to something else? And here, let's take advantage of the fact that we have a whole bunch of you guys. So some of you try, let's try different learning rates, and you can report your results and see if any of us gets, you know, better performance, right? So the learning rates, let's try the following values, okay? I'll just write them as a comment here. So the one that we're using right now is this one, right? So also please try 0.0001. You can try that one, or try 0.003 or 5. That should be the same. And also, I guess, try 0.01. You just never know. 0.003. Yeah, so I'm just adding a 0 or removing the 0. Do you see what I'm saying? In now, if you go with 0.001 or 0.003, you're gonna have to give it more epochs probably, because think of it as it's taking longer to get there, okay? But it might be more precise. So I'm going to try 0.003, okay? So you guys try something else. And I'm gonna have to give it more epochs for sure. So I'm gonna give it about 500 epochs. And I'm gonna use my multi-layer perceptron. Is this clear with everyone, guys? So let's go ahead and try this one. I'm also going to I'm gonna clear this and do another split. Okay, so let's go ahead and run it. Okay, so I have learning rate of 3 zeros and a 3, 500 epochs. Yeah. So this is something that I play with a lot, the learning rates. Okay, so there it is. It's training now. 33. And we're just gonna wait. Let's give it, sometimes you gotta give it. You know, sometimes you could give it 500 iterations and it's not working, and then all of a sudden it starts to work. So you just gotta give it. Any questions while it's doing this?
So the reason.
Yeah.
Self-linear 1 is 11/8 instead of 11/1 is because now we're connecting it to the hidden layer, and that has to be 8/1. So we couldn't give it any other number. Again, the hidden layer has to end with 1 because you only have one output option with 1 or 0. Yeah.
So going to this definition, right? So 11/8 and 8/1. So which one are you
I'm
referring?
talking about 8/1. It can only be
Right, it can only be 8/1 because the last layer is the output layer and there's only one neuron currently.
Yes.
We're predicting one value.
Okay.
Yeah. And it can only be 11 because all of our inputs are 11. But here we can change this 8 to whatever, as long as it's consistent here and here is the same.
Thank you.
Very good. All right, so the learning rate, not great. The loss is still not great. I'm still suspicious, as I said, of that, not rounding. But I guess in theory, it could learn to round by itself. So there is that. If you think about it, it could learn that it should predict not 5.3, but 5.0. You see that? So I don't know. It should be smart enough with the right data to do that. We do have a lot of data, actually. Like 4,000 samples is reasonable.
What if we increase the backside?
Try it. I can tell you, try it. Any luck, guys? Did any of you finish? No? You tried 0.03, and what happened? What's the R square? 0.30. Okay, so no improvement there. Okay.
0.0001
Okay, well, what point? 3 zeros and a 1. Okay. So that's the highest we've gotten. So this is how it is. Imagine this is a competition. whoever gets the highest R square is winning. You see what I'm saying? We will do an assignment like that at some point, but not the first, one, okay? But this is the way machine learning works, is competitions exactly like this, and whoever gets the highest score wins, has the better model, basically. And that's what we're trying to learn what to do. Now, we still have 2 more architectures to try. So we probably have enough time for that today. Okay.
Is there a way to
Huh?
get it to- is there a way to get it to shift back to the best epic that it?
Shift back to the best epic. The best loss, you mean?
Yeah, the best loss for the epic.
What was the best loss that you got?
Bounce around. The 0.19 is still like the best.
Yeah, I mean, you could save that model. There's a way that you could every loss, you could save the model. It's called a snapshot or something.
Yes.
And then that way you can look at that one and say, okay, I'm going to retrieve this model. That's something you can do. I just haven't shown you guys how to do it. All right, so it's at 300. Let's let it get to 500. I mean, it seems like an easy enough data set, right? So we should be able to get good results. And so it's still doing. Is it still running for all of you as well? Yeah. Yeah. Guess while I'm waiting, I can start adding in what I lost. Okay, so looks like it finished. So let's see. So now really let's look at the R square. 0.3353, so not great. Continue not. How about you guys? Did anyone get 37?
0.38 was the best I got.
0.38. Okay, so you're winning now. You're the leaderboard, Jason. Anyone get over 0.38? No. No, all right. So what else can we do? We need to throw more machine learning at it, right? All right, anyway, this is a joke. All right, so what do we do? Let's think of a couple of things. So it's not deep learning. This is just a neural net, but it's a multi-layer perceptron, so we can do deep learning. The learning rate does not seem to be it, because all of us try different learning rates. We could give it more epochs, certainly, but I gave it a lot of epochs just now. So there's a thing called dropout. Let's try dropout. Why not? So dropout is a technique, okay, which basically means, you know how I said it's fully connected, right? Well, dropout is a thing that whenever you're running the model, it randomly drops some connections. So it only leaves certain connections and others it drops. And basically it means it only calculates weights for certain ones and not for the other ones. Do you see that? And the idea is to force it to learn with less. And maybe that'll help. Now, another thing is we only gave it 8 neurons in the hidden layer. Maybe we should give it fewer or more. That's another thing we can try.
Yeah, another thing there.
But if I add another hidden layer, then it's no longer a multi-layer perceptron. It is now deep learning.
Okay.
Because that's the definition of deep learning, one more layer. That's it. And we've basically arrived at what we want. Another thing is I'm using the activation function sigmoid. Maybe I should use another activation. You see how there's a lot of little tweaks that we can do. Now, what you suggested of the hidden layer, let's hold off on that, because that's like officially deep learning then. So we're gonna do it though. So let's just try dropout first, okay? I want to show you how quickly we can add it in, just so that when we copy for the deep learning, we'll have it also available. So dropout just goes in here, okay? In the MLP, let's add now self dot dropout, and that's going to be equal to nn dot drop out, and we give it a probability. So 0.25. So basically we want it to drop out 0.25% of the connections. You guys understand what I mean? So if there were like 8, think of it as there being 6 now. Okay, and it just ignores 2 of them, and it's going to update the weights just for those 6 paths and not for the 8. And it just keeps doing that, and hopefully that may improve results. Now we want to tell it where we want the dropout to occur. So we're going to say that it should drop the connections after this activation here. So we can do x equals self dot dropout. And that's lowercase. Dropout then takes in the x as input and produces, so that the network now has this dropout layer. Does that make sense? All right, so let's try this one. And we're just going to let it run. And while it's running, we're going to start writing the next architecture, okay? Which is going to be what Lenny suggested. Let's just go ahead and build a deep learning model. Our first deep learning model, which is going to be very trivial to write at this point. Okay, so yeah. So let's now I'm going to leave the learning rate that I have. I'm going to leave the number of epochs. Dropout is there now. Are there any questions about dropout? Everyone got the code? Okay. So let's run it. It's not that way. Instead, it's every iteration is dropping some connections, and it updates the weights based on that network.
Oh, okay.
So it's like, imagine that you have 8 roads and you're learning the good traffic pattern to have, but every time randomly, you're just closing 2 roads. And so traffic flows in those 6 roads, and then the weights get updated that way. Okay, and then the next iteration, randomly it blocks 2 other roads, and 6 are available, things flow and the weights get updated that way. At the end of the day, the weights get updated just with a network that doesn't have full connections, okay? So that can work sometimes. So I'm just showing you techniques that you can play with whenever you're building your neural networks. And you saw it's pretty easy to add or remove them, okay? All right, so while it's training, which is going to take a while, let's go ahead and follow Lenny's suggestion, and we're going to create a new architecture. So now I'm going to do control copy, and I'm going to create, as you might imagine, a deep neural network, which basically just means adding, other hidden layers. So this can be 1 to 10. Now, you don't have to have 10 hidden layers, right? For what, when we build things from scratch, although some models are very deep, like the transformer, etc., ResNet, they're very deep. But they took a decade or so for ResNet, or transformers have taken, 4 years to arrive at the good, something good. All right, let's call this one DLNet. And I'm gonna make it with 2 hidden layers. Okay, so it's gonna be a deep learning model with 2 hidden layers. 2 hidden layers. So let's write it out, and then we're going to draw it out. Okay, so DLNet, same idea as before. Yeah, so we need to have the init function and the forward function. We define our variables, and then we build the architecture here. Okay, so it takes DLNet takes X means and X deviations. We store those. We're going to have 2 hidden layers. We know that the first the input has 11 neurons and the output has 1 neuron. But we are going to have 2 hidden layers now. How many neurons do we want in each of those hidden layers? You see what I'm saying? So let's do
4 and 4.
huh?
Could be 4 and 4.
Let's do actually funnel approach. So I'm going to do 10. Oops. Here to 10, right? And then I'm going to add another layer that's going to be 6. Okay, and 6 to 1. So that last one then would be 6 here. But in between, we're going to need to add another layer. So I'm doing a linear 1 from 11 to 10. Activation function sigmoid. Now, that's something that we should probably look into changing. And now I'm going to add self.linear 2. Okay? And this is going to be equal to NN linear. And now we're going to specify that this is going to be what? 10, 6. Very good. This is an exam type question. Okay? Like this kind of thing. All right, so this also will have its own activation function. So in this case, we say self.activation. Please remind me if I forget to change this activation from sigmoid to other ones, okay? If I forget. So this one is activation 2. Since it's a good practice to do this because we might have different activations, okay? So, but I'm gonna make it sigmoid for now.
In one network, can we have 2 different activations?
Yes, we can.
Like sigmoid and some other
We
value?
can. Yeah, like for instance, I could make this one ReLU right here if I wanted to. Yeah, good question. But for now, sigmoid. Okay. Like that. And then this linear, of course, is now linear 3, right? So linear 3. And that's gonna, just to confirm, that will go from 6 to 1. Yeah, 6, 1. And then we're gonna leave the dropout in there. Does this make sense, guys? This is deep learning, okay? That's it. Think how simple it is, right? To go from a neural net to a deep learning. Now we declare the variables. Now we just have to specify the architecture here. So we've got linear 1, then we've got activation 1, then dropout, for instance, you could do that. But let's actually not use dropout again in the beginning just to see what happens. Then here I'm gonna do x equals self dot what? Well, I already have activation 1. Linear 2, right? Yes. X, and then I'm gonna do x equals self dot activation 2 x. Very good. And then linear 3 x, and that goes into y pred, correct? Yes. All right. So that's a deep neural network, guys. It's still processing there. So let's go to let's go to the whiteboard and just kind of draw this out. Okay. All right. So let's create this architecture, right? Neural network is what? The input layer is still the same, has 11 neurons, dot, 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 11, right? The output is still the same, 1 neuron, 1, correct? But now we have, this is now deep learning, a term coined by Jeffrey Hinton himself. Okay, so deep learning. Okay, because if it only has one layer, it's a multi-layer perceptron, it's not technically considered deep learning. Okay, it's some neural networking. But now, and it has to have an activation function, right? But now we are adding a second one, and we set this one, I think, is 10, and this one, was it 6? 6? Yeah, 6. So there's 10 neurons, dot, 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 and then there's 6 neurons, dot, dot, dot. Okay. Now they have activation. So remember, you can draw it out like this, and this just sigmoid. And then this one also has an activation, and that's sigma. And I'm not going to draw out the connections, but it's fully connected. All right. Every neuron is connected to another neuron. Got it? That's it. That's deep learning. All right, let's try it in a second, I guess. We have to first wait for the other one to finish. But yeah, we're just giving it more power. Now, there are other activation functions like TAN-H. There's also ReLU. There's also GeLU, actually a newer one. Since we don't have that much time left, let's actually, for this deep learning algorithm, let's use ReLU, and see if that improves results a little bit. Usually a lot of deep learning just uses ReLU. It's like the recommended thing, use ReLU. Okay. So let's go ahead, share the screen. Okay. All right, it finished. That's good. So then let's see what the results are. 0.24. So no, not good. Were we using dropout with it? For the multi-layer perceptron? I think we were. So I don't want to use dropout in this particular case. Yeah, so we were using dropout here. But I'm not using it in the deep learning network, right? So let's do it without. Now, ReLU, I can't remember how to write it, actually. You guys, you Google it, nn.relu,
Capital R, capital L.
capital R,
Small.
I am. All right. So let's just give it ReLU and see if we get an improvement. Okay, so it would be there, and it would be here, right? Oops. ReLU, oops. Like that. Okay, So we're gonna try DL net. All we would need to do is change this. DL net. Okay, and I want to go back to the learning rate I was using before. So this one, right? I could also try like this 0.005, but it's the 2 zeros is what I'm looking for. All right, so I'm updating that. I'm going to now load DLNet. Okay, and now I'm going to run it again. Oops. Here. No, I have a typo. Okay. Try it again. Okay. That was pretty quick, right? 0.63. Did you guys see that initially? Now, it might be that it's using the old model. So that's why I got a 0.63 because I didn't start from the beginning. You know what I mean? So the model maybe is from the previous. Maybe let's start it actually. Let me do this. I'm gonna restart everything because I want to see actually from beginning, from 0. Okay, so run. Okay. And you guys run it too, please. And I think that's all we're gonna have time for today. But this is the challenge.
Up with a 0.16 for one of the losses,
Point.
but it jumped back up again.
Jump back
but-
up.
So that's-
Relo, you already finished?
Yeah,
I found Relu was better than Pan H. Well,
Okay.
just by a little
yeah, smidgen.
smidgen.
Smidgen. Yeah. Okay, so minus training. Oh, no, it's starting at 0.79, right? So, okay. 0.38,
Mine started.
167.
167. 1. Huh? What's the R square? Is that what you guys are telling me? That's what I need, the R square. So I need, whoever gets like 0.4. 0.30, yeah, so not great. Oh, no. I do have one more architecture to try. I do have one more architecture. Something that I've learned. But I'm still like, my thing is I'm still obsessed with the fact that the numbers are 6, 5, 7, and we're getting 7.3, 7.2. That's bothering me. All right, so we've got 14 minutes. I wonder if we can do this last architecture. So were there any questions on the deep learning, how to build a deep learning architecture? The 2 hidden layers, any questions with that? Was it clear? Yeah, okay. All right, while because it's gonna do 500 of these, let's do one last architecture. And this is like, I'm at the end of what I know. All right, we're gonna try one more architecture. And then I'm gonna let you guys basically take this home and play with it. And maybe you guys can figure out how to get best results. How about that? And let's do a homework to see who gets like 98 gets an 8, everyone else gets a C, okay? I'm joking. But you know, do your best though, and we'll make it a fun homework of just do your best. See, but we got 13 minutes, so let me give you one last architecture that I know about. And it's actually an interesting one. Basically, we're gonna create an architecture which is two functions actually. F1 plus F2. F1 will be a linear model. F2 will be a nonlinear model, and we're gonna add them together, all right? And predict with that. So to do that, let's call it linear plus nonlinear net. So linear plus non-linear net. I may only have enough time to give you the architecture, obviously, because I won't be able to run it, okay? But this will be your homework assignment to kind of improve this. So how does this work? Basically, let's add a comment here and just say linear plus, I'll use one word, non-linear, okay? And so this is going to be reflected as F1 plus F2. Okay, so you can see you can start doing more things in your neural nets. All right, so same idea as before. I'm going to actually just start from scratch here so I don't get confused. Okay, I don't want to give you like wrong things. All right, so it takes in X mean and X deviations. Then we're going to store X means and X deviations in the variables. Okay, and now we're going to define the two architectures. So I'm going to define F1 here, and then I'm going to define F2 here. Okay, just two functions. All right, so F1 is actually pretty simple. It's just a linear network. So I'm going to call it F1 linear 1, and it's going to be equal to NN dot linear. And it would be what? 11, comma 1, correct? Yes, okay, good. All right. Then F2 is going to be some neural net. I'll just do the MLP, but you guys could do a deep learning network if you want as part of your homework. Just try it. So this is going to be F2 underscore linear 1, right? And that's going to be NN dot linear. And this would be, we're going to have, so because this is going to be an MLP for this example, it's going to be 11 by, yeah, but at this time I'm going to do it a little bit different. Instead of fewer, I'm going to give it more. So I'm going to say 11 by 14.
It would be more than.
It can. Try it. Try it. I mean, it's not going to break. So try it. And as I said, whoever gets the best result, you know, gets the A, right? The only A. So Joey, right? So, all right. So, so we're going to do F2 underscore linear. And so NN linear 11, comma 14. It's just an example. Okay. Then we're going to do self dot F2 activation 1. And this is going to be equal to NN dot, I'm going to go with sigmoid, but you guys can change it to relu. You know how to do it now. So I'm just going to say sigmoid, okay? Then self dot F2 linear 2, right? Linear 2. And this is going to be NN dot linear. And now it should be what? 14, comma 1. 14, comma 1. You can add dropout if you want, but otherwise you don't have to do it. All right. And that's the definition, right? So now we have to define this architecture here. Okay. So how do we do that? We're going to say, you know, I'll add the comment again. This is F1. So that's going to be what? It's going to be F1 equals, oops, sorry. F1 equals self dot F1 underscore linear. And the input to it should be X. Yep. All right. Then we're gonna do F2, right? The second function. So F2 is gonna be equal to self dot F2 underscore linear 1, right? Linear 1 and linear 1 takes X, yes. Then F2 is gonna be self dot F2 underscore activation takes an X, yes. Then F2 equals self dot F2 underscore linear 2. And actually, I'm making a mistake. It should be F2, right? Yes. Sorry, I'm trying to go fast. Okay, linear 2, this should be F2. Got it, guys? Sorry about that. So X goes in F1, X goes in here, but then this becomes F2. So then over here, it should be F2, okay? Sorry about that. So let me just confirm. F2 linear 1, X produces F2. F2 activation 1. So I'm missing, I knew I was missing. F2 activation 1 takes in F2 and produces F2. That F2 then goes into F2 linear 2 and produces F2, okay? And now the last part is Y pred equals F1 plus F2. Do you see that? The trick is that you're using a linear function to predict and an MLP to predict, and then you add those values, and that's Y pred. So the weights are gonna be modified in such a way that both things are considered. Do you see that? And this is a trick. So it might be that most of it is linear, and then there's this little bit that's nonlinear. And so you kind of have both models. Okay, try it out. I have seen good, magically good results with this. So let's see what happens. Yeah, go ahead, please. This, yes. They're both predicting one value at the end. And you're just adding. It's the middle of just F2. So F2 takes 11 and it goes into its own network to the hidden layer of 14 and then to the output of 1. And F1 is 11 to 1. So they're like two separate networks. Did I answer your question? So think of it as two separate networks, but they're added together at the end. What matters is that, remember, every iteration you're doing this and the weights are updated in this fashion. So it might be that the neural network in the end thinks, F1 is the most important. But there's a part that it's not getting, and it starts to adjust it just a tiny bit to improve the results. It's two networks, technically. Okay? Yeah, got it? All right. Yeah, so try this one, okay, guys? And that's gonna be all the time we have for today. I'm gonna save this. 0.38. Okay, so let me see. So I did this training. So now I'm going to evaluate our square. Yeah, mine is 0.25. Point? You got 0.4? Okay, at 300 epochs? Okay. Yeah, so as I said, guys, that's the challenge. Now, one thing that, as I said, I'm suspicious of is that it's producing 3.6, 3.7. The values are 3.5, 3.4, right? So there's something there to think about. Try all these architecture and see if you can get the best results that you can, all right? All right, so we'll stop here for today. And we'll continue next week. Good luck with the homework, and please, so this homework, we have an exam next Wednesday, right? Also, so do you guys want more time to work on this? Or can you do it? Can you study and do the homework?